Afternoon, everyone. My name is Professor Sadie Ali Ferreira. I'm the Power Engineering Technology Program Coordinator here at Maine Maritime Academy, and I'm really happy to see so many people here for the CO200 and CO300 presentations. CO200 is the PET industrial field experience that happens after the sophomore year, and CO300 is the industrial field experience that happens after the junior year. Students are first
about 20,000 to 35,000 pounds of steam per hour. We have two natural gas burning boilers and two oil burning boilers. So the problem I'm proposing to fix is that there are a little over 200 steam traps that are not being accounted for at the steam plant. And when they're not properly maintained, they will eventually fail. So a direct quote from my technical analysis is up to 50% of steam traps in a facility will reside in a failed state after just 1 year without maintenance. So the steam trap that we use at the steam plant are manufactured by Armstrong, and they are inverted bucket traps, which are mechanical. They tend to fail open, which will blow steam and essentially just move our production costs up, and it's a waste. So my method of data collection is, if you look under the steam leakage, which is section A, I got the averages of a small leak, a normal leak, and straight blowing steam. So a small leak is 9 pounds per hour, which is just one steam trap. And a normal leak is going to be 15 pounds per hour. And straight blowing is 33 pounds per hour. I use 8,000 hours per year because they are in continuous operation in the unit cost of steam. And you can see in my equation 1 how I figured out my costs. So if hypothetically we have 10 steam traps that have completely failed, we will lose $26,000 and $400 per year. And if, like the quote said, 50% of the plant's 200 plus steam traps fail, it would cost up to $264,000 a year. So we have a quote from New England Controls that would only be $10,000 to $15,000 to do all of the maintenance. The survey is free initially, and so it would be really cost effective to do this for our steam plant. My engineering analysis is to propose to first have them come in and analyze all of the steam traps and survey them, tag and map everything so we can keep track and we know when we've inspected them, trap size, trap type, manufacturer, and application. And I propose to do this around our plant's off season, which is in the summer. And because UMO doesn't have a huge budget for this, I would suggest to do it in sections, and it would be very cost effective for us. If only 10 were fixed, we would still be saving enough money to make the maintenance worth it. And in conclusion, that it would be very cost effective for the UMaine steam plant to go through with this, and we would be wasting a lot less steam. Thank you.
Hi, my name is Maxwell Tomlin. I worked at Robbins Lumber, or Georges River Energy. So Robbins Lumber is a sawmill that produces around 431,000 board feet per day. And the purpose of Georges River is to produce steam to the boards to dry the kilns. Every day they send about 20,000 pounds of steam per hour to these kilns. They also have a 8.5 megawatt steam turbine that's a Chola turbine. Currently it's getting, they're gonna take it apart this fall and put in a Siemens one because that one is basically shot the bed. It's no longer good. It's not producing the right amount of power for it. The people that I worked with at the plant it's a diverse group. One guy had one leg, and he was a 25-year-old boiler operator that he knew his stuff about steam, but as far as basically knew the operations really well. And another guy was a recent MMA grad. The schedule I worked was 7 days on, 7 off, so it was a relatively, when you're on working hard, and then you had 7 days off, which was good. A lot of the guys there have really said that's one of the best schedules they've ever worked because you get a full week off and then you come in and you're just on the job working. So my problem, when I first came in, they were under load due to low fuel. They weren't able to get fuel into the yard as they would like because of the amount of wet seasons that we had in the winter. So they were running about 1 to 2 megawatts lower than normal, which would be around 5 to 6. The price of fuel had also gone up quite a bit. Last year when I worked there, they were paying around $21 a ton for fuel, and this year they're up to $31 a ton. So with the price of their fuel going up, they also their megawatts are at a fixed rate right now at $100 a megawatt. That's just how they have it in their contract. So for my data, every day we get daily fuel reports. That's how much fuel we've used based off of our metering bin. So it collects how much tons per hour we use. Right now it's around 350 if they're at full load, and at this reduced load they're at about 260. So I was able to collect all that. They get daily power output reports that show how much megawatts you actually produce each hour. So I was able to compile those and create an Excel to show how that worked. So I studied the price of the chips. We also use a 962 cat loader, which uses diesel fuel, so you have to fuel that up every day. The price of that had gone up over the summer and had to come into effect. They use about 30 gallons of fuel each day during the summer while I was there, I was at about $5.20, which has to come out of their prices. So the cost of diesel per day was about $170, and the way I did it was you take the price of the chips that they pull in each day, and then the amount they get for the megawatt output, and basically cross-analyze that. And what I found was when they are at a lower load, they are actually generating more money based on the higher price of chips. And that's it.
Hi, my name is Kelsey Byrne, and this summer I worked at the Clearwater Wind site with NextEra Energy Resources. So this site was a wind site located in Miles City, Montana. I spent about 6 weeks out there. It will have, when it's finished, a total generating capacity of 750 megawatts, and it consists of 131 GE wind turbines, and that is their 2.5 and 2.8 platforms. And what was unique about this is it has a really long transmission line just because of the location of it, and so it has an 80-mile long transmission line. And at the end of construction, all of this power will actually be sent to Washington in Puget Sound. So this summer, my technical analysis was centered around this problem, which is since 1988, NextEra has not had an efficient or reliable way to track the development of wind sites. And this has caused the company to lose a lot of time and money due to miscommunications or things of that nature. And so my proposed solution was to use satellite imagery to track this. So I did a cost-benefit analysis to kind of conclude if it was worth it to use the satellite imagery. And I started this by first quantifying how much it will cost to get this imagery. I used the company ERM and Planet because one offered past relationships with NextEra, and the other one offered a much cheaper price for the same quality of product. And so I received a quote from them for about 6 weeks worth of imaging, and they did the math to conclude that you can see the cost of imagery for both of those. And that is based upon the assumption that from the beginning of a project to the end, it's about a year, which on average, that's usually what different wind projects take. And then I wanted to quantify how this imagery could save us money. So I went in and spoke to each of the superintendents at my site and had a conversation with them and asked, how much money do you think that the use, or how many hours do you think the use of satellite imagery could save you per project? And then I multiplied the hours that they had by their hourly rate. Well, using that to quantify it doesn't necessarily take into consideration the fact that we still have to have someone on site to do that job. In the future, depending on how well this works, it could be that one superintendent can take over multiple disciplines, or because it's through satellite imagery, we could have one superintendent oversee 2 sites. But the real kicker here is with the benefit for micrositing. So micrositing is when you go in and you see where everything's going to be laid out, you go on site, you do geotech core stuff, and kind of really lay out how the wind site is going to go. And the satellite imagery aids this a lot. And I was able to pull up the cost for micrositing of Clearwater 1 and then reduced it by 50% because in conversations with my manager, he believed that the implementation of this would reduce it by 50%, and that's where the real cost savings are. And so you can see at the end here the total benefit, even with ERM or Planet, both result in a pretty big benefit for the company. So in conclusion, I actually was able to give a presentation at the very end to a bunch of the executives in the company and made my recommendation that we move forward with the satellite imagery and overall choose Planet to use in the future. And as of a couple weeks ago, I heard back from them and we have signed a contract with Planet, which means that all of the satellite imagery is coming in for both of the Kossuth and Great Prairie, which are 2 of the largest wind sites for NextEra, and all of that imagery is being implemented into one of our platforms for use. Thank you.
Nope. Run this full screen on this thing again. Such. Yeah.
There we go. What's that? Why is he doing that? No, it's fine on the screen. Oh, okay. Okay, I was seeing it on this one. It looked different. Good afternoon, everyone. My name is Andy Cody, and this past summer I completed my CO300 co-op at Plant Franklin in Smith Station, Alabama. Plant Franklin is a natural gas combined cycle plant with 3 2-on-1 units totaling 1,857 megawatts and is owned and operated by Southern Power. So for my technical analysis, I performed a cost-benefit analysis substantiating the use of power augmentation. So in the southeast, during the summertime, there's a large demand on the grid due to the increased use of air conditioning. And so this use due to supply and demand increases the energy rates, which power plants can capitalize on. The problem with this, however, is during these higher temperatures, the air is less dense. So higher temperatures bring less density, so it's a lot, it makes it, the same amount of work needs to be done to create the same, more work needs to be done to create the same amount of energy, so therefore is less efficient. To get around this, Plant Franklin used Power Aug to make up for those lost inefficiencies. So what is Power Aug exactly? Power Aug is a process of robbing steam from the HP turbine, the exhaust of the HP turbine, and routing it to the gas turbine, and then injecting it into the gas turbine, which increases the torque on the generator and therefore increases megawatt production. However, since it's robbing steam from the steam turbine that could have been reused in the steam cycle, there's a loss in efficiency and therefore a cost. So that cost is a lost load and an increase in the heat rate. So my objective was to find if Power Aug revenue outweighed those costs and the lost load and the increased heat rate. So for my approach, I conducted my research. I utilized several resources. I first collected trend analysis data from OIS, which is our data historical database, where I collected info such as megawatts produced and heat rate at various loads. I then contacted our commercial optimization and trading department to get gas prices and peak pricing to base all my my numbers off of, as well as general information from our shared drive and operational manuals within our S drive. So using this data, I was able to compare the cost of the heat rate penalty and loss load to the revenue which we collected. Here you can see some of the work I completed during my analysis. To summarize this, I calculated daily, monthly, and peak cost of the heat rate penalty and loss load to get the total lost revenue from enacting Power Aug, and then compared that to the revenue gain, and then after I compared that, I was able to get the net revenue, which ended up being a net gain of $4,000 to $7,000 per day, or $600,000 to $1.1 million per peak season. So as shown here, it's very substantial additional income to enact Power Aug. As demonstrated before, even with the costs associated with the operation of Power Aug, the revenue generated significantly outweighs the costs and is recommended for Plant Franklin to continue to use Power Aug during the peak season, summer peak season times. Thank you.
All right, good evening, everyone. My name is Theodore Hallett, or Teddy. Tonight I'll be speaking about my CO300 cooperative field experience. So I did my co-op at Southern Power Company Plant Rowan. This is based out of Rowan County in North Carolina. It is a 1,000 megawatt plant, and it uses both combined cycle and peaking. Phase 1 is the peaking side, and that runs 3 GE7FA turbines. Those run on liquid fuel and natural gas, and the combined cycle uses 2 GE7FA gas turbines, and only one of those is liquid fuel capable. The other is just natural gas, and 1 Toshiba steam turbine. So the problem that I had to identify was the plant's installing a new fuel gas heater in their gas yard for the gas that enters the plant, and the plant wants to save money while doing this. So the two options that I came up with were piping out the combined cycle block, because they already have their own fuel gas heaters on the skids, or installing a new type of heater that has an integrated thermostat. So my data collection, I used the OIS point trend, and I also did dew point research, because the dew point part of it is why they heat the fuel before it goes into the plant. And I did equation research, which I had help from Professor Sarnacki at this school for that. And I contacted the head engineer at Piedmont to ask about the new heater that's being installed. So I had to find multiple things for my calculations. I had to find the mass flow rate of the fuel, the specific heat capacity of the fuel, and the temperature rise. The temperature rise I got from the Piedmont engineer, and the specific heat I got from a fuel report, and the mass flow I got from the OIS. And I used these to calculate the heat capacity of the heater. And with that, I could calculate the yearly cost with the fuel cost. And with the yearly cost, I could do the ROI equation, which is return over investment. In conclusion, the piping option had an ROI of 26% per year, and the new heater design with the thermostat had an ROI of 0.42% per year. So the plant decided to implement the piping option, as they will get their investment back in 4 years. Thank you.
Hi, my name is Ryan LaChance, and I did my CO300 project at ND Paper in Rumford, Maine. So I worked in the utilities department at at the Rumford Mill, which consists of a recovery boiler and 2 circulating fluidized bed boilers, which we burn biomass, tires, and coal, and each of them produce up to 400,000 pounds of 1,300 psi steam, which we send to a 90 megawatt double extraction steam turbine. So for the problem I had, as we all know, Rumford emphasizes efficiency. It's our main priority. And so my problem was to analyze putting a heat exchanger on the DA vent. So on the left is what we currently have, which is your standard DA. And then on the right is putting a heat exchanger, which having demon water going through it on the other side. And then also having vents to get all your NCGs out, and then having your condensed steam go back into the condensate collection tank for reuse. So I realized that since we have such a high flow of demon water going through, that the steam coming out of the DA isn't really enough to heat up the demon water. It's such a small amount. So instead I ended up figuring out the fuel savings by using the condensed condensate instead of using demon water.
So there's 5,700, or just under 5,700 pounds of steam coming out the vent per hour, which condensed down comes out to 682 gallons. And if you take the difference of the steam, the condensate temp versus the demon water temp, it comes out to 1,132 BTUs saved per gallon of condensate used. And if you multiply that by 24 hours a day, we end up saving 18.5 million BTUs per day. And then our fuel cost worked out to be $4 per million BTU, which comes out to just under $75 a day in fuel savings. And then also we have chemical savings by not having to treat the demon water since it's already treated as condensate, and that saves an additional $16 a day, coming out to a grand total of $90 a day. So I know it doesn't seem like much, but it adds up over time. And then the materials cost worked out to be just under $50,000, and the reason why there isn't the heat exchanger is because luckily at Rumford we have a lot of spare parts because the place is old. So I moseyed around and found a new one, or used one, and figured this one would work great. So that's why the cost remained relatively low, because if we, like a heat exchanger like that would be probably around 100 grand. So if by having a free one, it makes it so the payback time would be under 2 years, and even if you included a $150,000 installation budget, then it would be just right around 6 years. But in my opinion, I don't think we should add that because at the mill we have a lot of other bigger problems and a lot of other efficiency losses that we could use that capital elsewhere. So thank you. I'll set you up. Yeah, I might have to click on it again.
Here we go. Hi, my name is David McLeish. I worked at Sappy Somerset this summer, located in Skowhegan, Maine. So the issue we had was the natural gas price kept rising, and our boilers kept tripping because of biomass issues. So we had the traversing bin kept sticking up, and each time that happens, it's a 24-hour job to get it to unstick and put new bearings back into it. So the engineers at Sappy asked me to track the number of tons burned each day on biomass against the price of biomass and natural gas. So for data collection, I use Process Book, which is basically a overall view of our plant with the recovery boiler and the 2 hog fuels and the steam turbines. It shows you anything from natural gas price to the number of tons into the boilers at that point in time. It updates every minute, so it's pretty exact. From Process Book, I put all the data into an Excel sheet and accumulated it so that engineers could look at it and see how many tons we were losing a day. So the equipment failures that we had, our traversing bin feeds both the hog fuel boilers, and for whatever reason, the design that it is, the 2 screws come together and they get hung up on each other every once in a while. When I was there this summer, that happened 3 times. So that's 3 boiler trips, causing a 24-hour job to unstick the traversing screws and then get the boilers back up and running on bio. Because when the boilers trip, there's no fuel going into them, so you get to switch to natural gas. So just from June to August, there was a little over 36,000 tons of biomass that wasn't burned because of equipment issues. And the engineers that gave me the analysis, when I left, they looked over all my data and everything. They were pretty amazed at how many tons that we actually lost throughout the year. So they're going to try to work to put capital budget in for this fall to fix the equipment issues that we discovered. So they were happy with it. They were really surprised on how much we lost. And each time you boiler trip, you're paying guys double hour because it's overtime at that point, and you're losing money by the second. And we all know how mills are, and everything's about money. So the more money you lose, the less money you're making. So thank you, I appreciate it.
I'm not seeing my presentation on this. It says Montrum's next. I believe so.
Can I blank the screen by any chance? Can I blank the screen by any chance? I might, yeah. Says no. You did not submit an oral presentation. If you'd like to come see. What you submitted here is,
Oh, was I thought I just submitted this.
that's what I have.
My name is Jacob Mottram, and I did my CO300 experience at Maine Waste Energy in Auburn, Maine. This is a waste energy facility. It's a mass burn. We don't process trash before it goes into the combustors. We had a 5 megawatt output of the steam turbine and generator, and the two boilers produced 50,000 pounds per hour of steam. This plant was also a base load. So the problem for my technical analysis, it was brought to my attention that the emergency generator that we had on site was too small to start the plant up. You had to use CMP power to start both boilers up. We were also not black start capable. And the power required, I had to go around the plant and get nameplate data off all the equipment and the motors that were required for starting up of the boilers. And then I took that number and calculated over 80% of the power just to ensure that the generator was big enough to start the plant up. For my analysis, I sourced out a new generator and got that price. I calculated a payback period, taking into consideration power prices and the number of times the plant tripped and went black. I also calculated the fuel costs of the generator, and I calculated different power prices throughout different times of the year. And in the end, I calculated a payback period of 4 years. In conclusion, a new emergency generator would benefit the plant a lot. There are still some aspects that I could have explored. I didn't explore the black start capable part of the project. It would save money in the long run, and in the past they had deemed it not financially feasible. Thank you.
So, hi, I'm Allie O'Neill. I did my CO300 co-op at Southern Power Plant Rowan, and I was a instrumentation and controls intern there. So, Plant Rowan was in Salisbury, North Carolina, and they had 3 simple cycle, 2 combined cycle, and a steam turbine. The 2 combined cycle and 1 steam turbine were base load. The 2 combined cycle was a 2-on-1. And the 3 simple cycle were peakers, and it had a max output of 1,000 megawatts, and that was due to the permitting they had there. Yes. And it's a natural gas, and or depending on the time of the year, considering permits, it can also run heavy fuel oil, except for one of the combined cycles. So for my problem, the LP and HP steam flow indications were inaccurate due to the loss of head level in the sensing tubes. So that right there is a picture of an annubar, which is the instrument they used to measure the differential pressure, which then they used to create a steam flow rate. And so on the right is the current installation they had, and on the left is the manufacturer recommendation. You can't tell, they're upside down to each other, so our problem was that the way it was installed on the plant was incorrect. And they had tried to fix this before by putting under, you can't see it, but they tried to put a second isolation valve in there so that they could refill the sensing lines, and they were finding that that was not working. So I had talked to and emailed with some Rosemount engineers to help me explain the situation, and they gave me my recommendations. And then I worked with SPS Engineering to talk to them, see what they would do with it. I was also lucky enough to have, in this bottom picture, documentation from the first time they tried to fix it. So obviously it looks different, and their first fix was just the second isolation valve, and they made the sensing lines, which is those black tubes there, the same height. What I would recommend would be that they would follow the manufacturer's recommendation, which was 45 degrees off the bottom, and that the sensing lines are either level or coming out below the instrument. The other two recommendations that SPC engineering came up with were to just move the sensing lines from above where they are to level and or below where the instrument is, and or just replace the annubars with flow tubes, which would be hugely expensive and would take a lot of time. The manufacturer recommendation would only cost $11,500, and replacing the annubars with flow tubes and moving the sensing lines would cost $17,500, so just a lot more work and hugely expensive. So in conclusion, this is what we're going to do, and we're going to change this over to that. Included a picture, hopefully you guys can understand that. And when I left, we had created a budget for it, but a decision was not made. So I'm excited to hear what decision they will come up with in the future. That is it.
Okay. Hi, my name's Gene Pelletier. This past summer I did my CO300 internship at Penobscot Energy Recovery Company. So here's a description and a little bit about the environmental compliance about Penobscot Energy Recovery, PERC. It's a waste-to-energy plant in Orrington, Maine. Both of the boilers can produce, well, with a turbine, 25.3 megawatts. Each boiler is 133,400 pounds per hour, totaling 266,800. PERC uses a baghouse and a dry lime spray absorber to help reduce emissions. The baghouse is mostly for particulate matter, and the dry lime spray helps lower the SO2 emissions. PERC is also a zero water discharge facility as of 2014 and releases no water into the Penobscot, which flows directly along site of the plant. They also use many ash removal systems, which are just conveyors, and bring it all to a trailer that is brought to Juniper Ridge landfill. So I encountered a problem at PERC. There was many problems, but this one stood out to my interest. So PERC has a lot of spontaneously combustible material. We experienced this quite a bit, and it actually led to a 1-month shutdown throughout peak season. A large fire pump is used that produces 1,500 gallons per minute, and there's 3 pumps in this system total, all are in parallel to each other. The smaller pump, the jockey pump, is just for pressurizing the dead line that is not being used, no water flowing through it. The big pump is the main electrical pump that I was focusing on. This pump turns on automatically once it senses that there is a large enough pressure drop in the piping system where the jockey pump cannot handle. The other pump is a diesel, which is a backup for the electrical pump in case there is some sort of failure. So the biggest problem with this pump is that once it turns on, it does not turn off automatically. This means that somebody can go and open up a fire hose, the pump will turn on, water will be spraying out, and then they can close it and the pump is just sitting there cavitating. This is a big problem because this could not only lead to the pump failure, but you would eventually have cavitation bad enough in the pump where you'd have to replace the impeller and seals, which actually the seals are replaced at least once, sometimes 2 or 3 times a year. This repeatableness can cost quite a bit for the plant, and I was just trying to find a way to minimize the amount of cavitation time that the pump was experiencing. So I contacted Greg Scott of Trastacrow Machinery from Southern Maine for the cost of the shaft, which is about $9,000. I also found pump efficiency tests performed by Maine Fire Protection Systems, and those were provided to me by the safety manager at PERC. I gathered the cost and time to replace rotor and seals from the maintenance manager, Tim Kroll, at PERC. All of these pretty much were a day. The shaft replacement would have taken a day. The seal could have taken a few hours. It all depended on who was on staff and who could work on that type of machinery. In conclusion, I discovered that the pump was operated off of a PLC system, and I used some basic ideas from our automation class from last year to rewrite the PLC programming and add a timer on delay, which activates a coil to open a contact and shut off the main power to the pump after a 15-minute timer. I talked with both the superintendent of the plant and the safety manager and decided that 15 minutes was a suitable time, as we don't want the pump automatically turning off as soon as a line is closed, because they might have to use it right again. The total cost of adding the new system in, which involves a flow meter, would be about $4,463. This is already half the price of the shaft itself, let alone the seals and the possibility of repetitiveness. That's all.
Hello, my name is Andrew Roderick, and I will be presenting my technical analysis for CO300. This summer I worked 680 hours at Eco Maine, located in Portland, Maine. The picture to the right is Eco Maine, the waste energy facility. There's two boilers. The A boiler is located on the front of the building, and the B boiler is located on the backside. So Eco Maine is a nonprofit organization that is owned by 20 local communities around the Portland area. They currently have 73 community contracts for their waste. The plant is considered a base load plant that produces 14 megawatts of electricity. There's a picture of our turbine, as it was not there all summer. We haven't been able to see it yet, but I plan on going back maybe this winter break to taking a look. So Eco Maine has one turbine for both their boilers, which was Eco Maine uses roughly 2 megawatts of electricity to power their recycling building and their waste to energy facility. As previously mentioned, Eco Maine has two boilers capable of producing 72,000 pounds of steam an hour. The boilers produce steam at 650 psi and about 750 degrees Fahrenheit. My technical analysis is over their selective non-catalytic reduction system, often referred as a SNCR system. The SNCR is a combustion emission control system that injects urea or ammonia into the furnace to reduce nitrogen oxides. At Eco Maine, we use urea. The problems that Eco Maine currently their current system has are that many of the pressure gauges are broken. The flow meters are not reliable. There's no room for automation. The equipment is old and is ready to be upgraded. And lastly, the urea lances run 24/7 when the boilers are online. Those are our flow meters and our pressure gauges right there. Replacing the SNCR system with a newer one would bring the NOx reduction down from 160 parts per million to nothing higher than 120 ppm. The raw gas was measured by M&S Umweltechnik from March 13th through the 17th, 2022. They found the range of NOx to be 250 to 300 ppm. Doing the math, that would be a 13 to 16% efficiency increase with putting a newer system in. The newer system would have 2 levels of lances. We currently only have 1 level of lances with 2 lances on both sides of the boiler. The newer system would have 2 levels of lances with 6 lances per level per boiler. The lances would also be automated, so they would kick on and off depending on which part of the boiler would need it most, depending on the temperatures inside. In conclusion, the newer SNCR system would be way more reliable with multiple injection points. The lances would be automated, which would mean they would not run all the time, which would make them last longer, and the consumption of urea would also be minimized. Maine will have more flexibility with future stricter regulations, and there will be less time spent troubleshooting and replacing failed equipment. The picture here is what one of our current lances looks like. There's 2 of them on each side. And there would be 3 lances instead of 2 on 2 different levels. That's it.
My name is Amos Anderson, and I did my CO200 this summer. It was my first co-op, and I did it at Newington Station in Newington, New Hampshire for Granite Shore Power. Newington Station is a single unit steam turbine that can produce up to 422 megawatts, and the boiler, one utility boiler, puts out almost 3 million pounds of steam per hour. And to achieve 422 megawatts, we use 16 fuel burners, 1 on each corner of the boiler on 4 levels. And we do number 6 fuel oil on the bottom, followed by natural gas on the top 3 levels. And this is a peaker plant, so we primarily run in the heat of the summer, which was when I was there, and then they run in the cold of the winter quite a bit. The safety procedures were pretty common among most power plants. The PPE was very common. You can't really walk around the plant without your boots, your glasses, hearing protection. There's a lot of job briefing that I found out about. All the supervisors meet before many jobs, and then the supervisors brief us on all the work that we have to do. Incident reports. Incident reports help protect the workers. You report incident reports when something happens on the job. Confined spaces. I did a lot of confined space prep. So before anyone enters the confined space area, we have to do a lot of tests to make sure it's safe. The confined space report is posted outside to let whoever's entering know that it's safe to enter. Lockout, tagout. There was plenty of that. Basically every job, there's lockout, tagout on any equipment that you're working on. And we were also right on the river, so we had some facilities that were actually on the water, and we had to follow the U.S. Coast Guard working near the water permits. My work experience was all over the place. Every couple of weeks I changed departments. I worked with operations for a couple of weeks where we did rounds, and I got to monitor the control room along with the control operator, so I got to learn a little bit of that. I worked with the instrument and electrical department. We did a lot of work on PLCs. We did a lot of work in the cabinets. And I also worked with maintenance. We did a lot of the housework, making sure everything was tidy. We worked outside, and I worked with the mechanics for quite a while. We did a lot of repairing valves. We did a lot of pump work. We did a lot of maintenance on the pumps themselves that had to be done routinely. And overall, it was pretty interesting because I got a lot of experience in all different fields. Some good qualities I learned for those of you going in. Be attentive. I learned that kind of being aware of what's going on around you is a lot better than just kind of sitting around. Even if you don't know what's going on, if you're attentive, sometimes you'll actually start to pick up on it. Be flexible. Like I said, I worked in 4 different departments, and I didn't really know where I was going each day when I walked in, but I was flexible enough that I could easily move into it, and it worked. And I was very open-minded. Keep an open mind even when it's not the best. If you stay open-minded, then you can usually make the best of it. Some bad qualities to have that I learned. Omniscience. You don't know everything. You might have taken Professor Burton's STEAM class, or you might be AWS certified by Mark Legal, but you don't know everything when you go to this plant. Being reluctant and bashful also does not help you. If you're not asking questions, then you probably won't learn as much as you should. They obviously know that you don't know everything. I've only been in school for 3 years, and it was all pretty new to me, even though I'd been through the schooling. Once you see it in person, it's kind of all new. My overall experience, I got a lot of general knowledge. Like I said, you can learn a lot through slideshows and from professors in class, but actually seeing it and doing it in person is a whole nother thing. It went pretty smoothly. I was pretty prepared for it, and overall, it was pretty informative and helpful to actually take the knowledge I've learned in school and actually apply it and be able to fit in with what the industry is like. Thank you.
Okay. Good afternoon. My name is John Noah Bell. This summer, I did my co-op for Pixel Specialty Solutions located in Maine. It is a combined cycle plant, 2-bus system. So the peaking plant, which was built in 1999, has 3 151 B12 gas turbines, each with its own HRSG. The gas turbines are dual fueled. The HRSGs can produce 3 different types of steam, HP, IP, and LP steam. The Hercigs at max load, at max, can produce 450,000 pounds of 900 psi steam, 250,000 pounds of 160 pound steam, and 50,000 pounds of 60 psi steam for the paper mill and its own auxiliaries. This right here is the picture of the peaking plant, also that we mainly refer to as cogen at the mill. That's kind of like the general slang for it. So in the paper mill side of the mill, right now we only have one steam turbine that's running. It's a GE Series 6 EX2000, and it has the capability of producing 25 megawatts. It also has a 160-pound steam extraction, and 40,000 pounds per hour of that steam is sent to the paper mill. The paper mill usually uses upwards of 200,000 pounds per hour of steam when number 4 and number 5 machine are running. The rest of the makeup steam is provided by the peaking plant. Okay, so my day-to-day job at the plant was mainly just doing routine rounds on and monitoring the feed water system, so anything from demineralizers to checking wastewater numbers and checking the condensate pH hardness, and etc. I also did some routine maintenance on pumps and compressors at the plant, anything from like changing oil and stuff like that. Throughout my summer, I was also able to work on a turbine shutdown for the steam turbine. I was able to do multiple shutdowns and startups of the gas turbines up to cogen. I was also, it's safe. But I was able to work on a turbine wash and brine wash also at the same time, so that was really good. So for safety, at the mill, it's a very rigorous process that I wasn't expecting at the beginning. We spent 4 straight whole days going over, things that I didn't even see at the mill eventually throughout my time. But it was really good, and that was reinforced even more when I went and met my supervisors. Communication was very open at the mill, and I found that at any time that I was maybe a little unsure or needed, a little more clarity on something to do, I found there was always someone that could help me out, so I felt safe in anything I was doing. So overall, I think it was an awesome experience. In this just little 5-minute presentation, I probably couldn't even touch upon what I learned this summer. I had a great time. I definitely recommend it for those who are looking to get some experience with combined cycle plants. That's it. If you have any questions, you can definitely ask me after, and if you're really crazy, you can read my technical report, but I don't know if I'd recommend that. Thank you. Where am I going again for this?
Wait, this is not mine. No, I have to change it. Oh. Oh, perfect. All right, thank you. All right, so good evening. My name is O'Neill Brown. I was a part of Wheelabrator Concord. This was my first cooperative industrial field experience. I'd also like to mention that I may say Wheelabrator or Wind Waste Innovations because Wheelabrator is actually a part of this large merger by Wind Waste, established in 2016. There's also 14 other plants that are involved with that. These are a few topics I'm just going to discuss. My plant description, the safety program established, and my work experience. So this is a Wheelabrator Concord is actually a waste to energy plant. We actually provide our own waste collection service for commercial and residential waste. We're 24/7, 365. We're a small baseload plant. We run, like I said, all year, except for an outage. We have usually 2 outages a year, or sometimes, I got to experience a couple emergency boiler shutdowns. We burn about 575 tons of municipal solid waste per day through 2 Babcock and Wilcox boilers. We produce 14 megawatts in a single Dresser-Ran turbine and Dresser-Ran generator. Our steam output is, so we're permitted to run by New Hampshire law at 69,800 pounds, but our boilers ran at 69,400 pounds because, we wanted to provide a little barrier for ourselves. Some safety standards. So actually, Wind Waste has 5 pretty solid company standards or company core values. One of these is one team, another's pride matters, make a difference, act with courage, and most importantly, safety on purpose, which we call at the plant SOPs, and you could actually use these. You would put in SOPs and you could win prizes and stuff. It was kind of cool. It was a neat little thing that the company did. So for my safety training, I had to go to orientation in Portsmouth, New Hampshire at the Wind Waste corporate office for 2 days. You kind of went over some basic things, stuff such like IT, sexual harassment, some just safety protocols, basic safety protocols. After that, I actually had to, once I arrived at the plant, I had to do about 2.5 days of online safety training. This also consisted of 2 pretty thick books. One was environmental safety, and the other one was personal safety. This took a while. I kind of thought, maybe I shouldn't have gone to, they could have mixed the corporate and the plant thing together to make it a little bit quicker, but how they do it was, that's how they do it. No, PPE was pretty standard, for most plants. Hard hat, uniform, safety glasses, gloves, boots, hearing protection. Always had to have my uniform tucked in. We actually had a lot of corporate people coming to our plant for tours. Probably once a week we had this happen, and they were very strict on everyone wearing all their proper PPE. Don't miss any steps. Don't be caught walking around without your safety glasses on, things like that. We also had to wear Tyvek suits. This was in required areas. It's a full white suit with a hood, and sometimes we had full face masks, half face masks. I actually, unfortunately, had to wear these a lot, and they're extremely hot. So for my day-to-day, my work experience, I was part of a lot of plant cleaning. We were actually one of the cleanest plants out of all 14, which was, felt good, but it was a pain sometimes having to clean, very tedious things. One of the most interesting things for me was the boiler tube replacement. This was because of a failed boiler tube during a hydro test. I was able to be a part of, watching one of the outside contractors by the name of Nemo, and you can see in that top picture on the left, that's actually him in the penthouse welding one of the superheater tubes. Another thing was the MRS, which stands for Metal Recovery System. We had to, in these bottom pictures down here, you can see saturated ash would go onto this belt right here and go down to the trucks, and we had to actually replace these scrapers, which would scrape off all this wet, saturated ash. The whole belt was replaced. It was a pretty big ordeal. It took about 8 hours of the day. We had a company come and do that. These scrapers, me and a coworker, actually me and 2 other coworkers were a part of this. We had to replace, you can see in that bottom picture, there's a yellow piece right on that belt. So that scraper, and then this is the secondary scraper. You can't really see it. It's hard to get a picture. It's kind of confined space. And then emission system maintenance. That was just carbon calibrations, calculating pounds per hour of carbon, lime slakers, maintaining that, and the SDA lances. As for my conclusion, my overall experience, it was good. I feel like I could have learned a little bit more. Also, would I do this again? Depends on the kind of job I would get, the position that I would be taking, because I didn't 100% enjoy the position that I was in at the time. But that's it.
I don't know what to click. Is there like a percent button? Is there a percent button? I don't know where it is. All right, my name is Brendan Cavers, and I did my CO200 internship at Penobscot Energy Recovery Company in Orrington, Maine. There's one General Electric turbine and generator set, and the generator is capable of producing 25 megawatts of power. We have 2 boilers. Each one is capable of 133,400 pounds per hour of steam. On site, we receive municipal solid waste, and it is ground up through grinders and turned into refuse-derived fuel. And this plant only runs one of their boilers 24/7 and keeps the other one on standby. We had required PPE, which included long sleeve shirts, long pants, steel-toed boots, safety glasses, a hard hat, and we only had to wear hearing protection when we were in the powerhouse. I got to experience a lot of lockout tagouts because we worked around conveyors, and it was probably the most dangerous thing there. And anytime we were near them at all, they had to be off and locked out and tagged out. And we learned all of the safety stuff during our safety training during the orientation. I forgot to switch slides. So my experience there was great. I absolutely loved it there. The other operators who were full-time, they really took our education and experience seriously. I worked as a B operator or boiler operator, and probably by the 4th or 5th week, I was able to valve in and valve out a boiler by myself to get it online. And to conclude, it's 133,400 pounds per hour of steam for each boiler. I worked as a B operator all summer, and we primarily burned RDF, which was just ground up MSW. And there were safety guards around the conveyors everywhere because they're very dangerous. Thanks, that's it.
Hi, so my name is Brandon Coates. For my CO200 field experience, I worked within Nine Dragon Paper in Rumford, Maine. I'm going to talk to you guys a little bit about the plant, their safety program, and my role within the facility itself. So at Nine Dragons, they produced about 640,000 pounds per hour of steam using black liquor from the pulp process. We would send that steam to cogen to create about 90 megawatts through their steam turbine. So within their safety program, I spent the first couple weeks in between online and in the field training, and probably another month on top of that to work as a bee operator. There's the normal personal protective equipment, hard hat, face shield, earplugs. And then whenever I would do anything out in the field, there's always safety procedures. There's standard safety procedures, would have to go through those. Also, with before and after the shutdown, we'd have to do a lot of lockout and tagouts to make sure everything was isolated. So within my work experience, I worked as a bee operator. I did my first 2 weeks there. We jumped right into a shutdown. So I worked with the senior operators to do lockout and tagouts, confined space entries, did a lot of hull watch, which was a drag, but I worked as a bee operator, poking the boiler, doing black liquor testing, a little bit of water testing, and assisting the A operator or the field A operator whenever needed. And it was a great experience. I touched everything. I looked at everything. I could run around, do whatever I wanted. It's great to see a lot of that stuff, especially during the shutdown. I got to see inside all the evaporators, even inside the boiler, precipitator, penthouse, all of it. It was really interesting to see. It really opened my eyes to what we've been talking about for the past 2 years. So in conclusion, it was a really great experience for me. I really connected a lot of the dots from the classroom to what I actually saw within the industry. I would love to go back and really learn more. I kind of walked in a little undergunned. There's a lot of stuff in that boiler room that I was not quite ready for. And I just really started to connect the dots, and I would love to go back and really keep going in with that experience. Thank you.
All right, so my name's Dawson Critchley, and I completed my CO200. There it is. My CO200 industrial field experience at Woodland Pulp LLC, owned by International Grain Investment Corp. Basic plant description: it outputs 48 megawatts. That's including the 10 hydro turbines that we have. 7 of them are at the on-site dam, and the other 3 are at an off-site location, Grand Falls. That's made up by 2 steam turbines, the 40 megawatts. Turbine number 10, manufactured by GE, is 23 megawatt average output, and number 11 is a 17 megawatt average output. Steam capacity, 1250 kilopounds per hour. That's made up by 2 boilers, one of them the number 3 recovery boiler and the other number 9 power boiler. Number 9 is the swing boiler, so that changes if we need any extra process steam or if the header level's dropping. Basic safety. I kind of wish that Professor Travis Wallace was here because this is actually his younger brother, Chris. He's a good guy. Basically, that's your PPE that you'll see everyone wearing if they're outside of the operator's room or outside of the plant in general. Rule of thumb for red and yellow caution tape, anything behind yellow you should use caution. Anything behind red, there's a possibility it will kill you. Hot work and confined space entry. Your supervisor will fill out those permits and they must be hung at the job site. Proper PPE in designated areas. This changes in certain areas like lime kiln, you need to wear double eye protection. And I believe in the around the chipyard you also have to wear double hearing protection because there's a lot of loud equipment there. We have NIS come in and do asbestos removal weekly, and we also have chlorine dioxide alarms that have separate tones and lights so you can identify that hazard. My work experience, I got to dive into project management a little bit. We did a booster pump upgrade for the liquor unloading pit. We had to size the pumps ourselves, me and my supervisor, and basically figure out, what we needed for flow and pressure. I did some data entry as well on the hydro turbines. I basically plotted the average megawatt output per day and used that combined with the price of power in Maine so I could figure out how much money we were saving by keeping them up and running. I also did weekly utilities trainings with MMA alumni John Cook. And my conclusion here for any freshmen and sophomores that stuck out the presentations, 3 steps to succeed at future co-ops. Never pass up any opportunity to learn or improve on yourself. Don't stress over not knowing the plant, it's expected of you. And be outgoing, don't be afraid to ask for help. Supervisors would much rather have you ask questions than go back and fix the mistakes that you made. And 9 out of 10 people from my experience were very friendly and willing to do that. So, and this is just, I don't own the pictures, so that's my works cited. And thank you for your time.
My name is Joey Koreski, and I did my CO200 at West Brock, Missisquoi Mill in Sheldon Springs, Vermont. It is a paper mill that turns recycled paper into paperboard. So at the mill we have 4 different boilers. One is a 1952 Wickies water tube boiler. That one runs at 600 psi superheated steam. Then it is desuperheated, and there's a PRV that brings it down to 165 pounds before it goes into the system. Number 2 is a 2008 Cleaver Brooks fire tube boiler, package boiler. It also runs at 165 pounds. And boilers 3 and 4, they have a common wall. They are a 1923 Babcock and Wilcox boiler. They run at 165 pounds. And paper machine 1 is in 1914, and paper machine 2 is 1924. So everybody calls it the operating museum. The mill was built in 1895. So for safety, your standard stuff. You have 2 full days of training. Your typical lockout, tag out, confined space. And they had 100 days accident-free when I was there, which I guess to them seems like a lot, but the plant that I was at was 4,000 days. So for work experience, I worked with the engineering team. I kind of took the boiler room under my wing because they didn't have anybody that really covers the boiler room. And one thing I learned there is everybody is so worried about the paper machine staying running that they overlook the boiler room. We've had quite a few problems, and they're like, just run it, it's fine. And it's not how it works. So I did a lot of CAD drawings of the systems. One I had to do was the continuous blowdown system because the overflow tank ball kept getting crushed because there was too much pressure. In conclusion, it was a very good internship. I learned a lot. The boiler operators really knew what they were doing. They were very helpful to me. Yeah, it was pretty good. Yeah, that's all I got.
Good afternoon. My name is David Dingley, and I'm part of the Power Engineering Technology major. And this past summer, I was enrolled in the CO200 Cooperative Industrial Field Experience. And for my experience, I was employed at Pixel Specialty Solutions, and it's a paper mill located in Jay, Maine. So basically, the plant operated as a combined cycle plant. We also had a cogeneration plant that possessed 3 gas turbines, each of them having a heat recovery steam generator, or you can call them HRSGs. A single unit put out 30 megawatts to the grid, and we produced high pressure, intermediate pressure, and low pressure steam. The max steam supplied by the HRSGs for the high pressure steam, it was 450,000 pounds per hour. For the intermediate pressure steam, it was 120,000 pounds per hour. And for the low pressure steam, they produced 50,000 pounds per hour. The gas turbines can burn natural gas or number 2 fuel oil. Although when I was at the plant, we never burned fuel oil, we only burned natural gas. The paper manufacturing process is a 24/7 process. We had at least 1 gas turbine and 1 steam turbine running at all times. For safety, I mean, when I first got there, we had a whole week's worth of safety and training. And we went over stuff like PPE, hazard environmental training, fall protection, fire protection, and like lockout, tagout. The mill supplied us with hard hat, safety glasses. We were responsible for closed-toe shoes and stuff like that. For the hazard environmental training, I was properly trained on like chemicals or any hazardous waste that the mill possessed. For fall protection, we were properly trained on how to use a harness and where they were located around the mill. Fire protection, we were showed how to properly operate 3 different kinds of fire extinguishers and where those were located around the mill. And we were given our own set of locks and keys in case we experienced any procedure to prevent like an untimely startup or equipment that has been taken out of service due to functioning issues. My work experience was, I was pretty much all over the place. When we first got there, we had to do the air compressor and turbine rounds. Basically, for the air compressors, we recorded data such as like outlet temps, oil level, and pressures on a little SKF handheld device. For the turbine round, we took bearing temperatures, case pressures, like, recorded the hydrogen purity, all on a sheet of paper. For the demineralizer regens, usually the demineralizers would break due to high silica levels. So if that happened, then we would need to valve out one, valve out another one, or valve in another one, and then perform a regen, basically a rinse down on the demon that broke. Water testing, I mean, we tested the turbine condensate, condensate from the paper machines, and we tested for hardness, conductivity, silica, pH. And for the startups and shutdowns, the only startups or shutdowns that went on were the combustion turbines at the cogeneration plant. When this would happen, I was given the opportunity to walk with the operator and just basically saw how the process was done. Would I do it again? Yes, absolutely. I mean, before actually seeing it in person, I thought all this stuff was kind of a myth, kind of like learning about it and hearing about it, but really never getting the chance to see it. I learned a lot of stuff just about gas turbines, steam turbines, and the basic general knowledge of a paper mill or power plant. And recommendations, I would ask as many questions as you can. Strive to learn more, and don't be afraid to ask questions and jump right in. Thank you.
All right, so my name's Aiden Doherty. I did my presentation and co-op experience with CO200 at Wind Waste, Wheelabrator, South Broward, because we were going under rebranding. So we had 3 Babcock & Wilcox 750 TDP boilers with potential to add a 4th, and each of those boilers could actually process 194,000 pounds of steam a day. All 3 of those boilers were coupled to a General Electric 66 megawatt hydrogen-cooled condensing turbine generator. And we also actually had one thing that was very plant-specific was our air-cooled condenser. Because we're in such close proximity to the airport, Fort Lauderdale Airport, we weren't allowed to have a cooling tower, so it essentially was an 11-fan giant radiator system that we used to cool all steam processes at the plant. We had 3 spray dryer absorbers. They each had a design temperature of 300 degrees Fahrenheit, and they sprayed lime slurry mix to combat emissions. We had 3 Snaker reduction technology systems, which sprayed urea into the boilers to combat NOx. And then we had a powdered activated carbon system, 3 of them each, which inject carbon to knock out emissions as well. And then we had 2 19-ton P&H overhead cranes that helped to move a lot of the municipal solid waste, special waste, all of that. We also had we had the DEA come in a couple times and do drug burns from Miami and everything, so I got to observe that, which was very interesting. And they are all coupled to the 197-foot concrete stack with that future fourth flume for the 4th unit. And I actually got to observe, they had the county come in because we rent the land and everything, the company rents the property. And the county came in to kind of start the analysis process of putting in that 4th boiler unit because they need it. So our safety program, this was Wind Waste's kind of own callback to what they like to do, and safety on purpose was one of the biggest things that they drove into us. I did the corporate internship, kind of step on bringing group where I went up to corporate, and then I got to the plant and they put me through their Win Academy program, which lists 2.5, 3 days of safety, to go over and everything, PowerPoints and whatnot. And then they have that Safety on Purpose program, and that program was actually very beneficial to the plant because anybody on the plant, whether or not you work there or not, you can actually submit a Safety on Purpose report. And each week there would be the weekly report that got picked, and then company-wide there would be the monthly reports and everything from own employees, which is very cool, and you'd be given spins on a wheel so you could get $25, $75, $50, $100 and whatnot. And then we had job hazard analysis, JHAs, job safety briefings if JHA wasn't required. We had to wear PPE. They actually sent me to Red Wing and got me new boots, which is pretty cool. Hard hats, glasses, ear protection at all times throughout the plant. So my work experiences, if you look, you'll see an office in that picture. As soon as I was brought on, the day operations crew that I was kind of brought into, they were remodeling an office for the vice president of waste to energy for their southern region. So I got brought on to do that. That's the after picture of the office after we installed everything and whatnot. We did multiple rounds in the SDA systems. We did lube oil conditioning rounds. And then you'll see on the furthest picture here closest to me, we did boiler number 2 walkdowns because we had, in our bull nose, we had a couple water tubes blow out, and then in the corners of the boilers as well, we had some water tubes blow out. And it was really just, at this waste energy facility, it was doing everything you could possibly do. Especially being in South Florida, it rains every day. So if you can burn trash in South Florida, you can burn trash anywhere, which was kind of drilled into me, which is really cool as well. They did take big safety measures for anybody coming into the plant as well. Because you're in South Florida, the plant standing temperature was 126 degrees every day. We had our Buffalo Forge units go out, which was very bad, and it was 163 degrees in the plant that day. So they make sure that we drink water. And in conclusion, I would definitely do it again. I got extended a job offer from the company to go back to the plant. It was a really good environment to be in, family-oriented environment where you really just fit in, and it was great. And yeah, that's about it. I had a good time. Thank you.
Is this the right thing? I'm not sure. I tried. Yep.
We're going to, and then go back.
Sorry for the delay. My name is Tara Morrison. I did my CO300 co-op at Maine in Portland. Maine is a mass burn waste energy plant located in Portland, Maine. And my chemical analysis was over the my technical analysis was over the chemical dosing system. So as an introduction, Maine this summer we had our turbine outage before the co-ops got there, and it went pretty badly. It ended up in quite a bit of insurance litigation, so what was supposed to be a 2 or 3 week turbine outage turned into a multi-month turbine outage. So we had to run on the dump condenser, which is what they normally do. It happens once every 7 years, and obviously we had a little bit of problems with it. The dump condenser, while rated for the full steam flow of the plant at 150,000 pounds per hour, couldn't hold the pressure over 100,000 pounds per hour. So we were having quite a bit of issues running our normal amount of MSW through the boilers. So I looked into trying to raise that so Maine could burn their maximum amount of trash that they're allowed to, even though they weren't making power. So what I focused on was the chemical dosing system. The dosing system that they're working with right now is pretty rudimentary. We only were running our hypochlorite system, and it was just metered through a needle valve that the operators would open and close at their discretion. So this would cause the cooling system to be overdosed and underdosed pretty frequently. As you can see, this is a picture of the outside of our cooling tower. You can see the algae growth on that is caused from being underdosed, actually pretty extremely underdosed. So my solution was to automate the system, which was actually automated in the early 2000s. The system had just fallen in disrepair after quite a few years of not being maintained properly. So I collected data from our boilers, all of our information inside Maine to see how much we could save doing this. And we'd already gotten quotes from our chemical manufacturers that showed that we could implement this for around $12,000. As you can see in this diagram right here, hypochlorite's only really useful at pHs under 8. So once the pHs rose, especially in the summer months when it got hotter, you had to switch to hyperbromine. So this is a separate chemical that we were not dosing this summer, and that had impacts when the pHs got above 8. So this new system would automatically switch from hypochlorite to hyperbromine when the pHs got higher, and this could save Maine a lot of money. This would allow a pretty big improvement on the efficiencies. From literature published by the chemical manufacturers, you could bring up to a 15% increase in efficiency for your cooling tower, although this seemed pretty high to me. So my calculations were based on a very modest 2.5% increase in cooling tower efficiency. So with that 2.5% efficiency increase, Maine could save upwards of $1,000 a day. So that would come out to about $360,000 a year in savings. Obviously, this would only be while the turbine's out, because when the turbine came back, we'd be able to run at higher efficiencies. But Maine would still have the benefit of having a new chemical dosing system and save money on chemicals and time for the operators dosing it manually. So in conclusion, having less algae running through the equipment will also make healthier equipment, as well as extending the life of the cooling tower. This would have an incredible return on investment, making its money back in less than a month, and it would make a much more effective use of chemicals. Thank you.
CO200 and CO200 students. Did anybody want to ask any questions to any of our presenters before we get going? Or if you want to